Hello everyone and welcome to this video. This is the third and final video regarding the transformer architecture. In the first one we saw the theoretical aspect or the intuition. Then the second one we saw the math, and now we will try to build a simple pet or example project. So the goal of this project is to show the transformer by building one from scratch in PyTorch. We will not just copy code. We will conduct a scientific experiment in two phases. So the first phase is algorithmic verification. We will train the model to reverse a sequence of numbers. So if we input like 1, 2, 3, 4, we should get 4, 3, 2, 1. This proves the model can learn logic and structure without the noise or complex language data. In the second phase, semantic application. Once we verify this part, we will apply the exact same architecture to a Thai English to Italian translation task. So by the end of this notebook, hopefully we will get the fully functional debugged transformer capable of generalization. We can see the architecture. So it's the same one as the one in the paper, as we said. The encoder side, the input, we do the embedding, positional encoding, multi-head attention, add and norm, feed forward, etc, etc. We know all of this. We saw it in the previous two videos. Okay, so let's get started. The first thing is we set up the environment. As we said, we will use PyTorch for the tensor operations. We will also auto-detect if the GPU is available to speed up the training. Okay, we're using CUDA. Okay, so let's go to the architecture. The key components are the input embeddings. So we will convert the tokens into vectors. This allows the model to learn the mathematical relationship between words, because neural networks do not understand strings, they understand numbers. And then we apply positional encoding, and then the multi-head attention. Self-attention, so each word will look at every other word in the sentence to gather the context. And the multi-head is we split the attention into different heads so the model can focus on different things at once. And then we stack these layers n times to create deep understanding. So this is the input embedding class, where we will perform the embedding using this function from the PyTorch. Now we will scale. Remember, from the image, after doing this we will scale. Now we are in this part. And now we are in the positional encoding phase. This is all in the encoder side of the architecture. So we do some dropout to prevent overfitting. We use the sine and cosine waves. So after this class is initiated, we should expect in a phrase, we know the order of each word, where is it, because remember that in the attention or the transformer, everything is computed side by side, so we do not have order of time. That's why we perform positional encoding. And then with the forward layer, we add position vectors to the token embeddings, so now they're together. Now for the attention mechanism, in the multi-head attention block, We set the number of heads, and then we do the like the query key and value multiplications. This is the dot product to calculate the similarity. And now we apply the mask. So we don't see the future values, so the model does not cheat. In the matrix, the upper triangle, we would set it into -infinity. So once we do the softmax function, it turns them to 0. And then we concatenate the heads. And now we go to the feed forward layer. This is pretty standard. This is the residual layer norm. Now in the encoder block, we will set it up using what we used here. Okay, so we have the attention, feed forward, residual layer, two residual layer norms, and then the forward. And now for the decoder block, we will have two multi-head attention blocks, the feed forward block and then the residual layer. And then we do the forward calculations. Okay, so now to put all of this to the transformer architecture, we do the embedding, positional embedding, encoder, decoder, and then the projection. This is the forward for the encoder and the decoder. So let's run this cell. And now after building all of this architecture, you can pause the video and read through them line by line. So now to experiment, as we said, we will do two experiments. One, we put an input of sequence of numbers and we expect the model to give us the reverse order. So ABC becomes CBA. Why this matters? Because if the model simply memorizes the training data, it will fail on new sequences. If it learns the algorithm of reversal, it will generalize to numbers it has never seen. So for the hyperparameters, we use a smaller vector size for speed, 8 attention heads for the parallel focus, and 5000 epochs. So this is because to heavily train the model, not just to guess. Okay, we generate random data, we pass it through the encoder, decoder, and now we initialize the model. We'll use the cross entropy loss for the loss function, add optimizer. This is the model, and the vocabulary size is 20, so between 0 and 19. And now we train the model. We expect to see the loss function decreasing. Once it's doing that, let's see the training process. So we have 5001 epochs, and each time we will do the forward pass, calculate the loss, and then do the back propagation. And then we will do the inference test, initialize it, and then test it with 8, 12, 15, 7. So we expect the output to be 7, 15, 12, 8, 12, 8. We expect to have this output. Okay, so now we just wait for the model to finish training, and we see the test result. Okay, the model just finished training, and for the test we failed the test. We expected this number, but we got this number. Let's try to add like more epochs for the model train more, the double, so 10,000. If that's not the problem, and then we will go back and try to investigate the error. So let's run it again with 10,001 epochs and see. Okay, so with 10,000 epochs we got the correct output. So it was a problem of we underestimated the learning compute. So no, it's okay. Let's go to the second experiment. It should be much simpler because we will set like a very small vocabulary for both the English and Italian. So now that we verified that the engine works, we will apply it to the language. We will use a very small or a tiny dataset to demonstrate the mechanics of tokenization to convert words into IDs and translation. So for the tokenizer, we build a simple dictionary mapping. Hello gets an ID, etc., etc. Training, since this vocab is small, the model should achieve near zero loss very quickly and gives us the desired output. So we will use this as the dataset. So we have two pairs, the English and the Italian translation side by side. In real world, we have very huge datasets like the entire internet or something. So now we will build the vocabulary from the dataset and add the special tokens that we talked about, like end of sentence, start of sentence, and the padding token. The padding token is to fill in the blanks. So let's say each word is a token, and we set like each input to be 10. So 1, 2, and the space 3. So we have to add at the end 7 more padding tokens, or 6, no, 5. Start SOS, and then this one, and then pad 5 times, and then the EOS, end of sentence. And so yeah, now let's train it. We'll use just 200 epochs because, as we said, it should be very simple. We should note that we'll use teacher forcing. So as we said, at each input in the decoder, we will force it to input the correct token, even if the model put the wrong one, predicted the wrong one in the encoder. This is just in the training. And then we test. So we will test hello world and expect it to give us ciao mondo in Italian. Okay, we can see the the loss is getting, oh, this is concerning. Maybe because we missed the hello world is at Dio Mondo. No, it's not correct. Do we have a spike in the loss here? Maybe because we have a very high learning rate. Let's add 2 zeros and make this like 500. Let's see. Okay, so that was the problem, a high learning rate and very few epochs. Again, I underestimated the we compute for the training. So now we got the correct translation from hello world to ciao mondo. I remember we can see like the loss getting slower, but we have some increases. Maybe the learning rate is still very big, because remember, if we have a big learning rate, we may skip the minimum value during backpropagation, so it's not very effective or good for us. So yeah, we successfully got the output that we desired. So that's it for this series, and see you in future videos.